In this lesson, we're going to look at how to solve some oblique triangles given two sides in the included angle and given three sides. To do that, we're going to use the law of cosines. So let's look at how we get the law of cosines first of all. What we have here is a triangle, and I'm going to label it ABC. And we're going to drop a altitude. So let's construct an altitude from, let's start out from angle C down to side AB. Now, the side opposite angle A would be side A. The side opposite angle B would be side B. Now, this would be side C, but since I've divided it into parts, I'm going to call this side X, and so this side would be C minus X. Okay, taking this part of our triangle, we've got our altitude, which we'll call H. We're going to take this, and just using the Pythagorean theorem, we know that H squared plus C minus X squared equals A squared. And let's go ahead, we'll multiply out C minus X squared. You can do C minus X times C minus X, and you will get C squared minus 2CX plus X squared equals A squared. Okay, and if we want to do some rearranging using our commutative property, we could say that C squared minus 2CX plus X squared plus H squared equals A squared. Just doing that kind of for some convenience. I just moved the H over to here. All right, let's take our other triangle, and we know from our other triangle that X squared plus H squared is equal to B squared, just using the Pythagorean theorem, the sum of the squares of the two sides. So now I know that X squared plus H squared is B squared. So I'm going to go over here and I'm going to substitute in all right, now what I'd like to do is to get rid of this X. So if I take my triangle here, I know that the cosine of A is equal to X over B. So B cosine A is equal to X. So I can substitute in C squared. Let me just undo that for just a second. I'm going to do some rearranging just to save a step. I know that B squared plus C squared minus 2C, and in place of X, I can put B cosine A is equal to A squared. So now I have where I'm solving for side A based upon side B, side C, and the cosine of sine A. This is called our law of cosines. And if we put our law of cosines, then what we have is that side A is equal to B squared plus C squared minus twice the product of BC times the cosine of the opposite angle, of angle A. We could go back and do the same thing, making altitudes to other sides, and we would find that B squared is equal to A squared plus C squared minus 2AC times the cosine of angle B. Notice the side you're trying to find, it's the sum of the squares of the other two sides minus twice the product of those two sides times the cosine of the opposite angle. So C squared would equal A squared plus B squared minus 2AB cosine of angle C. And this is our law of cosines. To use the law of cosines, let's just look at a triangle. Notice, if we're wanting to find side A, what we have to know is side B, side C, and the cosine of angle A. So two sides and the included angle. You can find the opposite side. To find side B, we have to know side A, side C, and the cosine. I didn't label those correctly, did I? Let me go back and do a better job of that. That was bad. This would be side B and side C. So to find B, I have to know side A and side C and the cosine of angle B, the opposite angle. So I need two sides and the included angle. To find C, I need A and B and the cosine of C, two sides and the included angle. So to use the law of cosines, what we need are two sides and the included angle. All right, let's go through and do some solving. Here we've got an angle, some sides and an angle. If we draw a triangle, we'll label it. And so we have that side A is 120, side B is 66, and angle C is 60. So as we look at this, we have two sides and the included angle. So what we can do is from the law of cosines, we can find side C. C squared will equal. And you can go through and say A squared plus B squared, but it's the sum of the squares of the two sides. Minus 2 times 120 times 66 times the cosine of 60. So we're going to use our calculator here. And we wanted C squared. So what we want is, that finds C squared. What we actually want to find is C. So we can go ahead and do second square root of 120 squared plus 66 squared minus 2 times 120 times 66 times the cosine of 60. And so we get that side C is 104. So C is equal to 104 inches. Now, we want to find an angle, and we want to go back and find that angle using the law of sines. So right here, we want to see if we can avoid, since we're going to be finding an angle using the law of sines, if you remember, that's when we have that ambiguous case. So we want to see if we can avoid that. We have two angles to find, angle B and angle A. What we want to do is to find the smaller angle, because if we find the smaller, we know it has to be acute. You can only have one obtuse angle. So if we find the smaller one using the law of sines, we know it has to be acute and we won't have to consider the ambiguous case. So here we're going to find angle B. because we know that it's a lot smaller. We know that angle A is the largest angle of the triangle. So it's possible that it could be an obtuse angle. So we don't want to find it. We want to find the angle that we know is acute. And that way we don't have to consider the law, the ambiguous case. So we're going to set this up that the sine of 60 is to 104 as the sine of B is to 66. So if we use our calculator, and again, we can go ahead and do that second sine since we know we're looking for an angle. So 66 times the sine of 60. Let me move this over. Divided by 104. If you forget to do the second sine, then just you'll have your answer, and then you'll just do second sine, second answer. So we get that angle B is 33 degrees. So now we know angle C, we know angle B. All we have to do is subtract from 180 minus 60 and minus 33 degrees. So we get that angle A is 87 degrees. So it wasn't obtuse, but we didn't have to worry about that. So angle A is 87 degrees. So now we've solved our triangle using the law of cosines. Okay, let's look at another one. We have that if we draw our triangle, and we will label it. We'll draw our triangle again. And we'll label it. Okay, so if we label this, we've got side A is 76.3, side C is 42.8, and angle B is 16.3 degrees. Okay, so what we can find then, we have two sides in the included angle. We can find side B. B squared is equal to A squared plus C squared. And again, I don't always go through and say the A and B there. It's the sum of the squares of those adjacent sides minus twice the product of those sides times the cosine of the opposite angle. And that way I only have to say the same thing each time and not memorize three separate formulas. Okay, again, we're trying to find B, so we know that we need to do the square root. So second square root, and we've got 76.3 squared plus 42.8 squared minus 2 times 76.3 times 42.8 times the cosine of 16.3. And we get 37.2. So side B would be 37.2. Okay, So now we know all three sides. We need to find our angles. Again, we want to avoid the ambiguous case, so we're going to find angle C first because it will be, we know it has to be acute. It's the smaller angle. So we'll say that the sine of 16.3 is to 37.2, its opposite side, as the sine of C is to 42.8. Okay, and I forgot to do my second sine, so second sine, second answer. So I get that angle C is 18.8 degrees. So C equals 18.8 degrees. So angle A is 180 minus 18.8 minus 16.3. So we get 145.6. Now, right here is a good example of what we're talking about of avoiding the ambiguous case, because we ended up with an obtuse angle. Okay, I just noticed that I entered that in my calculator incorrectly. It should have been 18.8. I can go back to second entry and arrow over. That was supposed to be 18.8. And then if I press enter, I get 144.9. So let me change this. 144.9. But again, this is still an obtuse angle. So I want to go back on this one to just show you why it was important to find the smaller angle first. If we had found angle A first, and we set up our ratio, the sine of 16.3 is to 37.2, as the sine of A was to 76.3. Now let's use our calculator here. And we would have said 76.3 times the sine of 16.2, or 0.3, divided by 37.2. And second sine, second answer. Okay, we would have gotten 35.14. Well, that would have been okay if it had been acute, and if we did the 180 minus the answer, notice we get the 144.9, which is the angle that we were supposed to get. So if we had found angle A first, we would have had to have considered the ambiguous case. But by finding the angle that we knew had to be acute, had to be less than 90, we didn't have to do the ambiguous case. So it's very important that when you find your angle using the law of sines, that you find the smaller angle first. Okay. We want to then look at what we do if we're given three sides. Up until now, we were given two sides in the included angle. But we want to look, well, what happens if we're given three sides? And how we go about solving our triangle. if we were given side A, B, and C? Well, if we take our law of sine that we just did, let's start with A. We know that A squared is equal to B squared plus C squared minus 2BC times the cosine of angle A. And let's subtract our side squared. So A squared minus B squared minus C squared is equal to negative 2BC cosine A. Well, we're trying to solve for an angle because we know all the sides. So we're going to divide both sides by negative 2BC. Now, when you divide by a negative, your signs change, so that's going to be a negative A squared, a positive B squared, and a positive C squared over 2BC. And that will equal the cosine of angle A. So now we have a way of finding an angle given three sides. So if we go through our law of cosines, then when you're given three sides, let me just write this one again. The cosine of angle A is equal to B squared plus C squared minus A squared divided by 2BC. We could go through and do the same thing with our other formulas. We'll find that the cosine of angle B is equal to A squared plus C squared minus B squared over 2AC. And the cosine of angle C is equal to A squared plus B squared minus C squared over 2AB. So if you notice what we have, it's the sum of the squares of the adjacent sides minus the square of the opposite side over twice the product of these two adjacent sides. So again, you don't have to memorize all three, just memorize the pattern. Now we need to decide as we start doing this which angle we're going to find first, because we're going to find an angle. We're going to find the first one using the law of cosines, and then we'll find the other two using the law of sines. So as we do this for cosine, if you remember, the cosine is positive in the first and negative in the second. It's negative in the third and positive in the fourth. So when we use the law of cosines to find an angle, there's not any problem whether that angle is acute, because our function would be positive, or if it's obtuse, it's going to be negative and show up. So we don't have to consider an ambiguous case when we use the cosine. It's going to return it in the correct quadrant. So what we do when we're finding an angle using the law of cosines, we find the largest angle first. Because if you have an angle that's going to be obtuse, it will be the largest one. And then you know the other two angles have to be acute. And you can use the law of sines and not have to consider the ambiguous case. So we always want to find the largest angle first. Well, let's take some triangles. Here we have us a triangle. We can label this side A, B, and C. We're given that side A is 13, side B is 14, and side C is 15. So we want to find an angle. Well, the largest angle will be opposite the longest side. So we're going to find angle C first. So the cosine of angle C is equal to the sum of the squares of the adjacent sides. So 13 squared plus 14 squared minus the square of the opposite side divided by 2 times the product of the adjacent sides, the sides that include that angle. Now, When we go to our calculator here, we're trying to find an angle using the inverse cosine. So let's go ahead and put that in. So second cosine, and we'll find the angle. Now, we have a computation here in the numerator. So we're going to have to put the numerator in parentheses. We're going to have to put the denominator in parentheses. So even though it opened up parentheses here, that's for the whole thing. You still have to put parentheses for the numerator. So we'll close the numerator, divided by, open the denominator, and if you don't put those parentheses, you're not going to get the right answer. So close the denominator, close the function, enter. Now, if you forgot to put that inverse cosine here, you do your computation, you'll get an answer, then do second cosine, second answer. So angle C is 67 degrees. Now, we know that A and B have to be acute because we've already found the biggest one. So it doesn't matter which one we find first. I usually stay in the habit of, when I use the law of sines, always finding the smaller one first, but it doesn't matter. So I'm going to find angle A. So I'll set up that the sine of 67 is to side C, which was 15, as the sine of angle A is to side A. Using my calculator, I have 13 times the sine of 67 divided by 15, and I didn't put my second sine, second answer. So I get that angle A is 53 degrees. And then all I have to do is subtract from 180 to get angle B. 180 minus 67 minus 53, and I get 60. So angle B is 60 degrees. So I found all three angles, starting out with the law of cosines and then going into the law of sines. To avoid the ambiguous case, when I used the law of cosines, I found the largest angle first. So one more. Whoops. That's a little better. Still not. So we have ABC. We're given that side A is 832 meters, side B is 623, and side C is 345. We're given three sides. We're going to use the law of cosines. When we use the law of cosines, we find the largest angle first. So we're going to find angle A. So the cosine of A is equal to 623 squared plus 345 squared minus 832 squared divided by 2 times 623 times 345. So I can do my second cosine since I'm finding the angle. Then I need parentheses 623 squared plus 345 squared minus 832 squared, close my numerator, divided by, open my denominator, 2 times 623 times 345. Close my denominator, close my function. So I get that angle A is 115.5. So it's 115.5 degrees. Now, I can use the law of sines. I don't have to worry about the ambiguous case because I've already found the only obtuse angle that the triangle can have. I found the largest one. So I'm going to find C. I'll set it up. The sine of A is to side A as the sine of C is to side C. So I have 345 times the sine of 115.5 divided by 832 and second sine, second answer. And get 56.7 degrees. Okay, now I've got a mistake here, and it's a mistake that uh, is common to make. I usually try not to make it, but if you look back up here with my problem, I left off my parentheses here. So what this found was the sine of 115 divided by 832. That's not what I wanted to find. So I need to go back and put that in again. It's 345 times the sine of 115.5. I need to close that parentheses divided by 832. Enter. And then I do my second sine, second answer. And I get that angle C should be 21.9 degrees, or if we round this off to the nearest tenth, it would be 22.0 degrees. And so that gives you a good idea of why that's so important. Watching your parentheses and closing things is very important, because if you don't, the calculator's only going to give you what you tell it. You're the brains, not the calculator. And so we have to be careful there. And now if we'll go back and we'll subtract, we've got 180 minus 115.5 minus 22. We get 42.5 degrees. So angle B is 42.5 degrees. And we've got our triangle solved. Okay, we want to look at a couple of applications and where we use the law of cosines. We've got one that says the diagonals of a parallelogram are 13 feet and 16 feet and intersect at a 60-degree angle. So if we've got a parallelogram and we draw our diagonals, okay, what we're told here is that they intersect at a 60-degree angle. Now, we have two angles here. We've got our angle here and here. One of them will always be obtuse unless you have a square, and then they're both 90 degrees. But we have a parallelogram, and so this one's going to be our 60-degree angle. Now, the lengths of the diagonals were 16 feet, that would be the longer one, and 13 feet. In geometry, you learn that the diagonals of a parallelogram bisect each other. So if we just look at our triangle here, then this side is going to be half of the 16, so it's going to be 8, and this side's going to be half of the 13, so it will be 6.5. Now, the reason I labeled this one is because it asked for the shorter side. So this is the side we're trying to find. If it had asked for the longer side, Well, then we would have used this triangle. This angle would have been 120 degrees because they're supplementary. This side would be 8, 6.5, and then we could find the longer side. So it just depends upon which side you're asked to find. So here we have two sides in the included angle. We'll use our law of cosines. So x squared is equal to 8 squared plus 6.5 squared minus 2 times 8 times 6.5 times the cosine of 60. And we're not trying to solve the whole thing. We're just trying to find that shorter side. So we can go back, and since that was x squared, we can do second square root. We have 8 squared, which is 64, plus 6.5 squared minus 2 times 8 times 6.5 times the cosine of 60, which we know is 1/2. So sometimes by knowing some things, you can just go ahead and enter them. But we end up then that the diagonal is 7.4. So the length of our diagonal is 7.4, and that would be feet. And not the length of our diagonal, the length of our shorter side. So we can use that then to solve a parallelogram using some theorems from geometry. Let's look at a problem that deals with navigation. Two ships leave the harbor at the same time. One ship is traveling at 14 miles per hour on a heading of 193 degrees, while the other is traveling at 12 miles per hour on a heading of 75 degrees. How far apart are they after 3 hours? So we have a harbor, and we've got some ships leaving. Now, as they leave, we are leaving at 193 degrees. Remember, we deal with that from north. So I'm letting this line be north, and one of them will go off on a heading of 193 degrees. So what ends up happening is from north, and do that. Okay, from north, we're going to travel around 193 degrees. That'd be 180, so just a little past south. And we're going 14 miles an hour for 3 hours, so we're going to go 42 miles. So the length of this vector would be 42, and our angle would be 193 miles. Okay, now we have another ship that leaves at the same time, and it's going 12 miles per hour on a heading of 75 degrees. So from here, it's going to go around 75 degrees. It's traveling at 12 miles per hour, so it's going to go 36 miles. And so it's going to go 36 miles. And this heading was, I'm going to make that pretty big, 75 degrees. Okay, what we want to know is how far apart are they after those 3 hours? We want to know this distance. Well, we've got two sides, 36 and 42. What we would like is an angle. And it's not too hard to find that. We know from the green all the way around to the black was 193 miles. From the green to the red, from north to this one, was 75. So the angle between these two is going to be 193 minus 75. And so that turns out to be 117 miles, or 117 degrees. I think that's actually 118 degrees. I did my subtraction correctly. So 193 minus 75, be 118 degrees. Now we have two sides in the included angle, so we can use our law of cosines and find out how far apart they are. X squared is equal to 42 squared plus 36 squared minus 2 times 42 times 36 times the cosine of 118. Using our calculator, we have that we're finding x, so the square root of 42 squared plus 36 squared minus 2 times 42 times 36 times the cosine of 118. So we get that they're 67 miles apart. So 67 miles after that length of time. So using our law of cosines, we were able to solve for that amount. And it makes a nice little problem. Okay, let's look at another one that deals with navigation. A plane is flying with an airspeed of 244 miles per hour with a heading of 272.7 degrees. The wind currents are at a constant 45.7 miles per hour in the direction of 262.6 degrees. Find the ground speed and the true course of the plane. Now, this is what pilots will end up having to do. So let's see what we can draw. We've got a plane, and so from north, we'll make this our north. Okay, from north, the plane is flying with an airspeed of 244 miles per hour and a heading of 272 degrees. So we're going to go around clockwise. Due west would be 270, so we're just a little past due west and going at 244 miles per hour. So we will look on that. I'm going to make that just a little bit shorter since I'm right here. 244 miles per hour. So we know that our angle, and I probably went a little bit past 272, but we'll make it okay. It'll still work out. Your drawings don't have to be exact. Just, we usually try to make them close. And this is 244 miles per hour. Now, we have a wind that's acting upon that plane. And so what we do is the wind acts the whole distance, so it acts on the plane. So what we're going to do is draw our north line again from here. And we have the wind currents are at a constant 45.7 in the direction of 262. So if we take our wind from here, it's going in a direction of 262, so it's not quite due west. And it's only 47.5. So we have our wind going off here. And this would be 45.7. And this angle here is 262.6. Now, what the plane is doing then is it's going in this direction because the wind is causing it to move down. It's trying to go here, the wind's pushing it down. So what we want to know is what is the airspeed, how fast is it actually going, and or what's the ground speed. What the instruments say we call airspeed. What the plane's actually doing is what we call the ground speed. It's what it's doing as it covers the ground. So we want to know this. And then we want to know what the course is. What the instruments say is heading, what the plane's actually doing is the course. Well, we've got two sides. If we knew that included angle, then we could find our ground speed. So let's see what we know about the angle that might help us. And in this case, we have to use a good many things from geometry. We will use our parallel lines. Our north-south lines are always parallel. And so if we can use those, then it makes the rest of our problem a lot easier. So what we have to deal with are our north-south lines. Now, from north around to our red line is the same as our red line around to south. Even though I haven't drawn south here, it still continues, and we could draw it if we needed to, if we can line it up. It continues on down. So from north to the red line is the same as the red line to south. Well, we know from all the way around to the red line was 272 degrees. South, take away 180, then would be the distance from south up to the red line. So if we did 272.2.7 and we subtracted the 180, we get that that angle is 92.7. So from south up to the red line is 92.7. So from the red line to north is 92.7. So if we take the 262, subtract what's outside the triangle, which is 92.7, then that leaves our angle inside. So if we take our 262.6 and subtract that 92.7, that's from the red line up to north, then we get that the angle inside of our triangle is 169.9 degrees. So the angle inside, and I wish I had drawn this a little bit bigger now, the angle inside is 169.9. Was 262.6. So yes, 169.9. So now I can find x. I have two sides in the included angle. Again, to find that angle, I used my north-south lines and the idea that parallel lines cut by a transversal, alternate interior angles are the same. So from north to the red was the same as red to south. Red to south was the 272.7 minus the 180. So that gave me this angle. Then if I subtracted that from the whole angle, that gave me what was inside my triangle. So now to find x, x squared is equal to 244 squared plus 45.7 squared minus 2 times 244 times 45.7 times the cosine of 169.9 degrees. So it's going to be that it's going to be second square root 244 squared plus 45.7 squared minus 2 times 244 times 45.7 times the cosine of 169.9. So we get 289 miles per hour is how fast the plane is actually going. That's its ground speed, 289 miles per hour. And we can see that the wind is going close to the same direction that the plane is going, so it sped it up quite a bit. It's going much faster than the instruments say. Now we need to know, well, what direction is it going? We need to know from north around to that pink line. Well, we know all the way from north to the red line. So if we knew what that angle was inside, the angle between the red and the pink, then we could subtract that from 272.7, and that would tell us in what direction the plane was flying, which is called its course. So we can use the law of cosines now to do that. We can set up that the cosine of 169.9 is to 289. Excuse me, not cosine. We're using the law of sines. So the sine of 169.9 is to 289 as the sine, and I'm just going to call that alpha, is to 45.7. So 45.7 times the sine of 169.9 divided by 289, and second sine, second answer. So we get 1.6 degrees. So alpha is equal to 1.6 degrees. So that means that our course is 272.7 minus 1.6 degrees. So we're actually flying on a course of 271.1 degrees. So that's how much off course we are. And this is what pilots actually do. Now, what they would normally do is if they really wanted to fly on a course of 272.7, then they would go backwards, they would counteract the wind, and they would find what their heading needed to be so that the wind would push them onto that course of 272. So what we're going to assume here is that they're really wanting to fly at 271.1, and they went backwards to find, okay, to do that, we fly at 272.7, and the wind pushes us onto that course. Let's look at another one that's similar to this, and it says the airspeed and heading of a plane are 140 miles per hour and 130 degrees. If the ground speed is 135 and its true course is 137, what is the speed and the direction of the wind? And normally we wouldn't be wanting to, we would know the speed and direction, and we would be trying to use this to find the course. But let's go ahead and look at this. So from north, I'll try to make this one a little bit bigger than I did that last one. It's a little hard to read. So from north, the airspeed and heading of a plane is 130 degrees. So the plane is going off in the direction of 130 degrees, which would be about here. We'll make this a little bigger. So 140 miles per hour and 130 degrees. Okay, that's 130. And this is 140 miles. Now, it tells us that the true course of the plane, that's what the instruments say, but what the plane is actually doing is flying off in a direction of 137 degrees, and it's going 135 miles per hour. So it's actually we're not wanting to do what we're supposed to do. It's actually going at 137. Okay, and if you remember what this one was, the first one, this was 130. And it's actually going at 135. So the wind is slowing it down some. See if I can do that a little better. Okay, what we want to know is what's the wind doing? We want to know, okay, the wind is pushing it this way. We can tell that. So the wind's got to be going in this direction. We need to know the speed of the wind, and we want to know the heading of the wind. We want to know from north what that direction is around to the wind, what our angle is around to the wind that's causing it to do that. Well, if we look at this, we know this side is 135, this side is 140. Mike can and we can figure up the angle between. Here, this was 130, this was 137, so that means that our angle between them is 7 degrees. So we know two sides in the included angle, we can find x. So x squared is equal to 140 squared plus 135 squared minus 2 times 140 times 135 times the cosine of 7 degrees. So second square root, 140 squared plus 135 squared minus 2 times 140 times 135 times the cosine of 7 and did something. Oh, I did. Okay, I can see what I did. I squared my 135, got carried away with that part. So let me just take that out and then press enter. So we get 17 Okay, so we get that the winds are traveling at 17.5 miles per hour. Now we need to know the direction that they're traveling, so we need to know this angle. Well, let's look at what we do know. If we know from north to the red line is 130 degrees. So from the red line to south, let's go ahead and extend my south line. Trying to extend it pretty straight. Not quite, but we'll pretend. So from the red line to south is 130 degrees. Well, so we know from here to here is 180, and from here to here is 130. So from north all the way around to the red line is 130 plus 180, or 310 degrees. So if we could figure out the angle between there, we could subtract that from 310 degrees and get that angle. So what we know so far is from north to south is 180 degrees. We know from south to the red line is 130 degrees. So that gives us a total of 310 degrees. Now, if we can find this angle inside, I'll call it alpha. If we can find that, then we can subtract it from the 310, and that will tell us from north to the wind. Well, we can use our law of sines. The sine of 7 is to 17.5, as the sine of alpha is to 135. So second sine of 135 times the sine of 7 divided by 17.5, we get 70 degrees. So the angle inside alpha is 70. So the wind is going at 310 minus 70, which is 240 degrees. So that's the heading of the wind. It's traveling at 17.5 miles per hour in a direction of 240 degrees. Okay, this is your law of cosines. When you're given two sides and the included angle, then you've got your law of cosines. You find the third side, and then you can use the law of sines, and you find the smaller angle first because you know it has to be acute. If you've been given three sides, then we have our law of cosines to find an angle, and you find the largest angle. When you're using the law of cosines, you find the largest one. When you're using the law of sines, you find the smaller one. And that will avoid the ambiguous case.